Hi there, I'm Josh Hugg, one of the head preceptors for Coast 226, and I'm going to try a new thing this semester. I'm going to try and create a video for every assignment that conveys why it's cool, why we care, and also to give you a little bit of a picture of how you can get started. So the first assignment we're going to talk about today is percolation. The assignment spec, for those of you guys who have not taken 126, will be on the assignments page. So there's a spec and a checklist. And the assignment page will tell you everything you need to know to complete the assignment, and the checklist has information about how you might get started, frequently asked questions, and other suggestions. But everything you really need to do to get the assignment done will be on the assignments page. So in this first assignment, you're going to be creating two classes. This first is this data type called percolation that's going to allow you to simulate the percolation problem. And I'll explain what that is in a moment. And your other class you're going to develop is called Percolation Stats, which is going to allow you to do experiments with the percolation class automatically. So let's talk about the percolation problem first. Once you finish your first class, percolation, you will be able to run our interactive visualizer as well as a number of other visualizers out there that will let you see that your program works and feel like, okay, cool, I can see this thing happening. So the interactive visualizer, my favorite, allows you to click. And when you click, you'll see that we're digging out little empty spaces. And you can imagine this is like digging out hollows in a planet, and now I have this big empty cave beneath the Earth. Something interesting happens when you dig at the top. We see that the squares are blue. And the reason for this is that you can imagine there's some vast reservoir of blue stuff at the top, perhaps water, that can flow into these squares. So as we dig, that blue continues to flow. Or, if there's an existing space that suddenly gets connected to the top, it will fill in as blue as well. And this is an interesting computational problem. How can you do this efficiently? And we're going to use something called the UnionFind data structure that you'll get to know very well with this assignment. So we keep digging and digging and digging. And one thing I'll note is there's this mysterious thing at the bottom that says does not percolate. What this means, well, we'll see it change in a moment, is eventually when you dig enough, there'll exist some path from the top to the bottom, and now what was once the ocean at the very top can now reach, I guess, the core of our two-dimensional flat world here. So at that point, we say that the world percolates. And then again, that just means that there exists some path from the top to the bottom. So you may ask, why would I care about this? Well, this turns out to be a common model out there for things like, say, oil drilling. A world which has a lot of open sites is a world in which when you dig, you can actually get to oil. And you can imagine that percolation means I've now dug into some reservoir beneath the earth, and I have gushing black stuff coming out of the ground. I can become rich. I can drive a car with that stuff. It's great. You know, everybody wins. I mean, in the short term, at least. And so what you guys are going to do, this first part of the assignment, is build a data type called percolation, where we have a method called isOpen that tells you whether or not a particular square is open or not. You'll have one called isFull that says, is it blue? Has stuff reached it from the top? There will be percolates, which says, does there exist a path from the top to the bottom? And finally, of course, we need some way to open up new squares. And you are going to build the class that's going to support all of that, to do all the smarts of the simulation. And we took care of the boring, gooey type stuff. So you might ask, what can I do with this percolation simulator? I mean, it's cool on its own, but you guys are going to primarily use it in a set of automated experiments driven by a class you'll build called Percolation Stats. And in this experiment, what you're going to do is start with an initially totally solid world where there's no open space, and you're going to dig out random squares one by one until eventually it percolates. And you'll be looking to see how long that takes. Now this may seem like a very arbitrary experiment, but it's in fact quite interesting for the following reason. From lecture, if we look at the slides, we have this picture here which says that. Let's imagine that we have a world where 40% of the sites are open, that is, stuff can go through them. If P is about 0.4, 40% of the sites are open, what you'll find is that a randomly generated world with that vacancy level is going to never percolate. I mean, almost never. You might get lucky. But when you generate a random world, pretty much not going to percolate. When you get up to maybe P of around 60%, you'll start seeing, okay, some of the worlds are percolating and some of them are not, right? As I am generating new worlds that have a more porous surface, percolation is more likely. And then once the probability of openness is 80%, so incredibly porous surface, we'll find that almost any world we generate is going to percolate. And you can see that very obviously visually here. that if you have 80%, it's, yeah, looks very percolating, right? What's interesting is that we can actually plot the likelihood of percolation. So we have a randomly generated world, and it has a porosity. You can imagine that P is how likely it is that the world has hollow spaces. And as that porosity grows, there's a sharp level where suddenly, kaboom, right? Almost any world with that porosity is going to percolate. So you guys might have heard of the idea that if the universe has a bunch of parameters, right? It has a fine structure constant, it has a weak nuclear force strength, and so forth. And if you tweak any of those parameters by just a little, we live in a sad universe where there's only black holes, or there never were stars in the first place, and there's no life, and it's very sad and lonely. So this is similar, right? You have a porosity parameter that as you tweak it, you go from a world where maybe industrial civilization could never have happened because there's no easy energy underneath the ground to grab, versus one where it became very easy, and then you can possibly destroy your ecosystem eventually by burning all of your fuel, if you have enough. So that's the kind of thing that you can probe here in some sense. We have a model for the connectedness of a planet's resources. So that's one situation which you might consider this. And what's really neat is this 0.593 value here, there's no known way to derive it from first principles. You have to run a simulation. So building the data type that you guys are going to build is the only known way, well, to efficiently compute this number. Let's talk about the percolation class that you guys are going to be starting with. You can think of percolation as a sort of weird accountant. We can give it commands, our accountant, and say, I want you to open 3, 5. And percolation will need to keep track of the information that in row 3, column 5, that site should be considered open for the purposes of all the questions that might come up. The most obvious type of question that we might ask percolation is a site open? And what I meant by accountant is you get to decide what the percolation class, how it's going to keep track of information. So for example, with isOpen, the easiest way to build a class that supports this is inside of percolation, give it a 2-dimensional Boolean array, start all the values out as false, and every time open happens, you switch that false from a true, and the way you support isOpen is you just give back the value in the 2-dimensional Boolean array. There's no thinking there. Where things get more interesting, though, is that percolation also needs to take into account information about connectedness to the top, right? So if I want to say, is something full, I need to be able to say, is there some path to the top? And again, you could just do it with the 2-dimensional array and run some kind of simulation every time someone says, is full. So for example, someone asks if some site at the bottom is full, well, you run a little simulation where you scan the top row and the next row, and you keep tracing forever, but your isFull method would be slow. Slower than we allow. And likewise with percolates, you can imagine, again, running some kind of simulation in real time every time someone asks a question. But you guys are going to do something smarter. You guys are going to use something called UnionFind, that I'm going to assume you know the basics of at this point, which allows you to support dynamic connectivity. You don't need to do a simulation from scratch every single time. And that means your code will, 1, be much simpler, and 2, be much faster. This idea of using existing implementations of data structures and algorithms to solve other problems is going to be one of the most important recurring themes, not just in our class, but when you program in your life, right? So if you want to solve the dynamic connectedness problem, you don't want to have to rewrite UnionFind every time. So let's talk about how we can translate between what our percolation class is supposed to do and what the UnionFind class here is capable of doing. So just like the percolation class, UnionFind has, you can think of as a set of commands you can give it. I can say, I want to union these two things. I want to state that these two things are connected. And then I can make queries. Are two things connected? I can find what component something belongs to. You may find that useful for this assignment. And also counting the number of components. And again, it's your choice about how you're going to use these things. Now I'll mention that in 226, most of the assignments are using existing implementations of data structures and algorithms to solve some other problem, though you also have a chance to implement some of your own. But it's very important that you guys understand how these things work. And striking that balance between when you guys should implement your own data structures and when you should use them is one of the tricky challenges in teaching a class like this, by the way. And you're of course always welcome to try and re-implement, and when I teach this class, I often go through and re-implement the data structures to make sure I really get how things work. Okay, so let's talk about translation between Percolation and UnionFind with some examples. Let's see. All right. So let's imagine that someone comes along and tells us, let's say this now is a call to our Percolation class. So maybe someone says, I want to open site 3.4. All right. And when I do that, our Percolation class needs to keep track of that information somehow. So we go to row 3, column 4, and we'll mark it as open somehow. And it's your choice, again, how to do that. Maybe with a two-dimensional Boolean array, but there's other possibilities that are equally valid or perhaps arguably better. Now the next question is, do we need to track, and that'll allow us to track the isOpen, calls to isOpen. The next question is, do we need to track anything about connectedness? I know a UnionFind is supposed to be involved here. And in this case, no. There's no notion of connectedness. This is not connected to any other cell. You can imagine if I dig out just one single square beneath the Earth in some discrete universe, it is not connected to anything. So we don't have to do anything at this point. Now imagine that another open query comes along. Now maybe 2, 4. So this is the next call someone makes to us. What our UnionFind structure, or sorry, our Percolation structure needs to do is we mark this side as open and almost the same color. And now we actually do have a union we need to do, right? Because we need to track the information that these two cells are connected so that future calls will be fast. So we need some kind of union call right here. This brings us to a very important point, that often when we use an existing data structure or algorithm implementation, the API for our problem we're trying to solve does not perfectly line up to the tool we're trying to use. So in this case, for example, we want to open a site, maybe site 2, 3, and that's going to generate union queries. Now, in UnionFind world, we don't think of the world as a two-dimensional grid. We say, I want to union object 26 and object 38, and that's what UnionFind allows us to do. So it thinks one-dimensionally. So we're going to have to be able to translate between the two-dimensional grid-based problem we have and the one-dimensional UnionFind tool, because that's what someone's already written. So back to our example here, we need a way to map from our two-dimensional grid to some kind of canonical one-dimensional representation. And luckily, there's a pretty simple way to do that. We can imagine giving each cell a number. So maybe this is cell 0. This is cell 4. This one's number 5. This one's number, let's say, 9, and so forth. And so by giving each one of these a unique number, it allows us to translate over to the UnionFind structure. So again, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hooray. So this one gets to be 14. This one is 19. And we could think of each of the cells in our original two-dimensional problem as having a unique number like this. Now this is just one possible way of mapping from our two-dimensional scheme to this one-dimensional. But if we use this scheme, which you're welcome to use, we would make the following union call. Union 14 and 19. So we have to be able to translate between one or the other. One thing of note is that a single open operation can in fact generate multiple union operations. Suppose, for example, we open to 2, so we need to somehow, I'm not showing this in terms of basic data structures, but somehow mark that as open. No new union operations happen, right? Because he's not connecting anything new. And now let's say that we get open 2, 3. So what'll happen now is we again mark this as open somehow. And what we'll observe is we need to make sure that these two things are marked as connected and these are marked as connected. So there's actually in this case going to be 2 union operations generated. And you will be responsible for figuring out how exactly that works. So in this case we need to union 12 and 13. And to union 13 and 14. And then we're good to go, because then our UnionFind object knows the truth about the universe. This raises an important note about modularity. if someone gives me this open operation, how should I encode create these union coordinates right here? So if I know that, in this case, we can imagine that effectively what we're trying to do is, if someone wrote a UnionFind operation that did what we wanted, we might say union 2, 2 and union 2, 3. If the UnionFind operation and the syntax are language supported, this would be the natural way to do it. We cannot do that, however. I'm going to very, very strongly recommend that you create a private helper method that looks something like this. Private int, maybe xy to 1d, and it takes int x and int y, and it generates a unique number that's one-dimensional. And I'll leave it to you to think about how to program or write that in code. But it should look something like this. So you really want to create a function like this. It's going to make your life a lot easier, I promise. And this kind of thing, this translation between APIs, if you can write helper methods that do that sort of thing, it will save you so much effort and time. It's one of my very favorite things. When I get code when I'm graded and it looks like this, I celebrate inside. Now something interesting happens. We finally get asked a question that's not just is open. Is open is silly. I won't even talk about it. Someone wants to know, is site, let's say, 2, 2 full? All right? How do we know? Well, one way is we could use our openness, run some kind of simulation as we on the fly, and it'll be very slow. Or that UnionFind thing that we have been building up this whole time, we can have it resolve the question. So here's 2, 2. We want to ask something about connectedness. So we need to make a connectedness query. But what should it be? Well, what does it mean to be full? Well, it means that you're connected to some site in the top row that is open. We know, of course, that we'll only be connected to open sites because we only create union calls when something's open. So really all it is are we connected to any top site? So the naive way of doing this would be, okay, well, I'm just going to say let's see, 12 connected to 0? Is 12 connected to 1? Is 12 connected to 2? And so forth, right? So we could just check connectedness to every cell in the top row. The problem with this is that it's going to make fullness checking linear time. In this class, 226 is all about efficiency. It's about doing things the best that we can possibly do. Well, we're reasonable. And if we look at the spec, there will be requirements along the way. For example, all methods should take constant time plus a constant number of calls to the UnionFind methods, UnionFind, connected, and count. Here we are making a linear number of calls. You will lose points, it'll be sad, your program will be slow, and we'll be sad too. Everyone will be sad. Instead, you should do something more clever. So as you guys know, it's been kind of the year of the one weird trick. So what better time to start learning such weird tricks for the use in algorithms classes. I found this one particularly horrifying, by the way. So the weird trick we would like you to use, or something like this, so in this case we're going to give it away. Later assignments we won't give it away quite so much, though this isn't the full story. You will soon, while you're working on this, encounter something known as backwash. And we encourage you guys to discuss with each other how to deal with this issue, but we'll get there later. The weird trick that you can use to make fullness fast and not require a linear number of connectedness queries is to create virtual sites. So in this case, I'm just going to make up a totally fake site that's not part of my two-dimensional grid that's connected to every top row, every item in the top row, and a virtual bottom site that's connected to every item in the bottom row. And then when we want to check if something's full, we're just going to do a connectedness query with that top site. So for example, if we created a special site up here that starts off connected to every top row, that's maybe number 9999, let's say, so our program will, we can imagine now what the constructor will do, is it will say union 09999. So the constructor does union 19999, and so forth. So the constructor does this when the program starts, so that all of that's ready. And that's fine, that doesn't break our rules. If you look at the specs, the constructor is allowed to take n squared time, so this is going to be cheap. Whenever we want to do a connectedness query, we want to say is full. In that case, connectedness becomes very simple. We just say is 9999 connected to 12. And we have our answer. And this whole picture here elucidates and gives you examples of the kind of things you will need to do to utilize existing algorithms and data structures. Of course, you should not actually use 9999 for your top site, because if your grid gets above 100 by 100 or so, you're really going to need that number. And that's one of the little implementation challenges you're going to have to work out. Here's another one that's particularly tricky. The virtual top site and the virtual bottom site. You may be wondering what this is about. That's so that you can support the percolates operation easily. You just see if those two sites are connected. One thing that will often pop up in student implementations is something called backwash. Let me show you how this works. Oops. So let's open up some sites. La la la. Okay. So we open this site and kaboom, backwash happens. It's as if we've created another super reservoir down at the bottom that will push things upwards, but that is not the correct behavior. And you guys, if you want full credit, there's a small penalty for this, but if you want full credit, you have to be able to fix this without making your code slow. And it's actually a pretty clever, there's several clever solutions, but it's pretty hard, actually, I'd say. But it's a purely intellectual challenge. It's not going to be something that's going to take a ton of code, and it's really interesting. In fact, on Coursera, we had a whole lot of people looking at this. We had a thread with 10,000 views. And you're welcome to talk to each other, to look online, to think about this however you'd like. And that is okay. So that said, have fun with percolation, and that is it.